Okay, good evening all. Welcome back. So this evening we will be discussing about the properties of moving charges and magnetism. Okay, so what are the impacts about moving charges? If a charge is at rest, we can say that it is stationary and some sort of electric field will be generated around the charge. And if a charge is moving from one point to another point, we can say that a current is developed, and with that current, we can have a magnetic field also around the current carrying conductor. So we are going to see the different aspects of these moving charges and what are the effects produced by the moving charges. Let's see. We have studied Lorentz magnetic force in this. Lorentz magnetic force. Lorentz magnetic force means a charge Q moving through a magnetic field B with velocity V experiences a force. That force is called Lorentz magnetic force. And that force is given by the equation. See this one. Magnetic field B, which is moving towards right. And the charge Q is present there. It is moving towards this direction with a velocity V. And there is an angle between this velocity vector of charge and the magnetic field vector. So magnetic field is always a vector because it is always having a particular direction. So charge is moving and that velocity also will be a vector. It is also having a particular direction. So the angle between velocity vector and magnetic field vector is marked here. And this is the force experienced by that particular charge when it is moving in a magnetic field. And we need an equation for this force experienced by that particular charge when it is moving in a magnetic field. Let's see what is that force. That force will be equal to Q, the charge multiplied by, charge is a scalar quantity, Q, the charge multiplied by the vector product of velocity as well as magnetic field vectors. These two are vectors. See here, velocity is a vector, magnetic field also is a vector. So the vector product of velocity as well as magnetic field. So that is the force experienced by the charged particle. When we write it in scalar form, that means without any direction, we can directly write it as QVB sine theta, because V cross B is equal to VB sine theta. So V cross B is VB sine theta. So we can write it as Fm, force experienced by a charged particle when it is moving in a magnetic field B. It is equal to QVB sine theta. So this force is called Lorentz magnetic force, Fm, Lorentz magnetic force. Theta is the angle between V and B that we have discussed here. So Lorentz magnetic force is equal to QVB sine theta, or Q into V cross B. QVB sine theta, Q into V cross B. F magnetic Lorentz force equals QVB sine theta. The theta is the angle between V, velocity vector, and B, magnetic field vector. There are certain special cases. If the charge is at rest, that means the velocity will be 0, velocity of the charge will be 0, V will be 0, then Fm will be 0. Lorentz magnetic force will be equal to 0 when the charge is at rest. So a stationary charge in a magnetic field, that means a charge which is resting at a point in a magnetic field, does not experience any force. So if theta equals 0 or 180, that is, if the charge moves parallel or anti-parallel to the direction of magnetic field. If moving parallel to the magnetic field, then theta equals 0. Anti-parallel, opposite direction to the magnetic field, then theta will be equal to 180. In both the cases, magnetic force will be equal to 0. Sorry. So the cases of V equals 0, then Fm will be equal to 0. Then if theta equals 0, that is parallel, 180 anti-parallel, in that case also Fm will be equal to 0. Then if theta equals 90, that is the charge moves perpendicular to the magnetic field, velocity vector and magnetic field, angle between the velocity vector and magnetic field vector is theta. And if that theta equals 90 degrees, that means the charge is moving perpendicular to the magnetic field line, then the force is maximum. So Fm is maximum only when theta equals 90 degrees. And the maximum value of that force equals QVB. Now, consider the force on a moving charge in uniform electric and magnetic fields. Force on a moving charge. If the charge is moving in a uniform electric field as well as moving in a uniform magnetic field, what will be the force on the charge that we are going to see? Okay, so electric field is represented by the letter capital E and magnetic field is represented by the capital B. Then Q is the charge. It is moving with a velocity V. Okay, so it experiences both electric and magnetic forces. If it is moving in an electric field, it will experience a force. If it is moving in a magnetic field, it will experience a force. If it is moving in electric and magnetic field, it will experience force due to both this electric field as well as magnetic field. Okay, the force experienced by the electric field, it is equal to QE. Q is the charge and E is the electric field intensity. The magnetic force there is, we have seen just now, F magnetic equals Q into V cross B. V cross means the B means the cross product of V and B. So the direction of F here, the direction of F here will be, the cross product means the direction of F here will be perpendicular to both V as well as B. Okay, so that is the meaning of that one. So the net force will be the sum of these two things, that is force electric plus force magnetic. That will be the net force on a charged particle moving in a electric field as well as magnetic field. So net force is given as QE. It is the electric force. This is magnetic force. Net force will be the sum of force due to electric field as well as force due to magnetic field. Okay, Q is a scalar quantity that we can take it out. We take it out, that capital E electric field plus V cross B. V is the velocity vector and B is the magnetic field vector. So this is called Lorentz force. Total Lorentz force. This one is called total Lorentz force. QE plus Q into V cross B, or Q as a common factor, then multiplied by E plus V cross B. This is called total Lorentz force. Then this is the total force acting on a particle when the particle is placed in both electric as well as magnetic fields. See this one, total Lorentz force, the concept. QE plus Q into V cross B. A charged particle is placed in both electric as well as magnetic field. It experiences force due to electric field as well as force due to magnetic field. So the total force is called total Lorentz force. It is equal to Q in bracket E plus V cross B. It's a very simple concept. Now, force on a current carrying conductor in uniform magnetic field. Uniform magnetic field. So here what we have to remember here is magnetic field lines are uniform in nature. Magnetic field is from left to the right, from left to the right. And here a current carrying conductor is placed. This is a current carrying conductor. This one is a current carrying conductor which carries a current in this particular direction. It is placed in a uniform magnetic field. It has got a cross-sectional area A. A conductor of length L, area of cross-section A, placed in a uniform magnetic field capital B. Then it experiences a force. Electrons means current is there. It carries a current means electron flow is there. Each and every electron is a charged particle. All these charged particles will experience a force. Okay. The force experienced by the electron will be equal to force experienced by each electron. Force experienced by each and every electron will be equal to Q into V cross B, because it is kept in a magnetic field. Then if N is the mobile charge density, charge density, and Vd is the drift velocity of charges, then total number of mobile charges will be equal to N into volume. N into volume. Volume is area of cross section multiplied by length. N L A. Then that equation reduces to NAL. NAL. This is total number of charge carriers. NAL multiplied by Q into V cross B. Instead of V, we can write Vd, that is the drift velocity, because these electrons are being drifted through that particular medium. So it comes to NAL multiplied by Q multiplied by VD cross B. That equation reduces to NA QVD into L cross B. Then the current I is given by the earlier equation. It is NA VD into E, but E here is Q. Okay, so that we can write like that. Then force on a conductor will be given by the final equation here. So in this equation, NA VD into Q, this can be taken as this one. NA VD into Q can be taken as I. This will be equal to I. So the equation reduces to F equals IL cross B. IL cross B. So the force will be perpendicular to both the current element and the magnetic field. Perpendicular to current element and magnetic field. Okay. So that is the force experienced by a current carrying conductor placed in a magnetic field. See this one, it's a very simple concept, Equation for force experienced by a current carrying conductor is IL cross B. I is a current, L is the length of the current element, means current element in the sense that length of the current carrying conductor, which is placed in a magnetic field. Okay, cross magnetic field B. So obviously the direction of force will be perpendicular to both IL and P. Out of this IL, current is a scalar quantity. This L is a vector quantity. So IL altogether is a vector because L is a vector quantity. Current is always a scalar quantity. Then IL cross B. Hope you understand. Okay. Then A cross B equals AB sine theta. Then we can write ILB sine theta here. Then comes the Fleming's left hand rule. We have the equation for the force, that is IL cross B. So the direction of force, what is the direction of force? Okay, this is a vector quantity, IL is a vector quantity, and B is a vector quantity. So force experienced by a current carrying conductor placed in a uniform magnetic field. So three things are there. One is force, then current, then magnetic field. So these three will have specific directions, and these directions are governed by the Fleming's left hand rule. So Fleming's left hand rule is very simple. This is the left hand. Hold the three fingers of your left hand in three mutually perpendicular directions like this. Okay, na? Three middle finger, forefinger, and thumb. We need three parameters. One is force, second one is direction of current, then the third one is magnetic field. So direction of current, remember, current is a scalar quantity. Direction of current means in which direction the current is flowing. Okay, so current always takes the direction of the carrier. So if you keep a carrier like this, the current will flow like this only. If you keep the carrier upward, it will flow like that only. Okay, so that is the concept there. So the Fleming's left hand rule states that hold the three fingers of your left hand in three mutually perpendicular direction: middle finger, forefinger, and thumb. Is it clear? Now you see. See this one. Middle finger. Middle finger shows direction of current. Forefinger shows magnetic field. Thumb shows direction of force. Middle finger shows the direction of current. So I, B, F. There is an easy technique to remember that I, B, F. Instead, F, B, I. Okay, na? FBI is a famous investigation agency. Okay, you all know what is this FBI and where it is located. So normally this FBI regulates the world. So on top, F here, B here, I here. F is a force, B is a magnetic field, I is the current. Clear? So Fleming's left-hand rule, the force experienced by a current-carrying conductor placed in a magnetic field. It's very simple. Okay. Now we move on to the next one. So this is the current, this one is the magnetic field, and this one is the force. Now, motion of a charge in a magnetic field. So this is a charge, magnetic field is kept there. B, the charge is moving towards right with velocity v. The charge is moving towards right with velocity v. And the force is downward. Okay. Okay. So if the velocity vector is tangential to the circle, then Fm equals QVB sine theta, Q into V cross B. F equals Q into V cross B. That is QVB sine theta. Okay, QVB sine theta. Then Fm, V and B are V and B. See here, V and B are perpendicular. Angle between V and B is either outward or inward. Now here it is outward. So V angle between V and B is theta equals 90. Sine 90 equals 1. So it is QVB. Fm equals QVB. The force is perpendicular to the velocity. Therefore, the charge will move in a circular path. This will be moving in a circular path. So, if it is moving in a circular path, the centripetal force will be provided by the magnetic force. Okay. So, the centripetal force is equal to Fm, magnetic force. Then centripetal force equation for centripetal force is mv square by r, that is equal to qvb, and mv by r will be equal to qb. mv by r equals qb. So only this you have to remember. Magnetic force is qvb, and that qvb is balanced by the centripetal force. QVB balanced by the centripetal force, then we get mv by r equals qb. All right. Okay. Now the time period, time taken for one complete rotation. See, it is going like this, no? Okay. If the charged particle is going like this. So what is the time taken for one complete rotation? So generally velocity, we can write it as V can be written as total distance travel, that is 2 pi r, divided by total time taken for one complete rotation, that is time period t. So t is equal to 2 pi r divided by v. Okay, t equals 2 pi r by v. And for v, we have developed an equation. 1 second. Okay, so 2 pi r divided by v. And instead of r, we can write mv by qb. Instead of r, we can write mv by qb. See this one, mv by r equals qb. So r will be, from this we can write r equals mv divided by qb. mv by qb instead of r. So 2 pi by v multiplied by mv by qb. So altogether we will write 2 pi m. This v and v get cancelled. This v and v get cancelled. So 2 pi m by qb. This is time period for one complete rotation. Time taken for one complete rotation. It is time period. It is given by the equation 2 pi m divided by qb. Then inverse of time period is frequency. Inverse of time period is frequency. Frequency equals 1 by time period, or inverse of time period. That equals inverse of time period equals qb by 2 pi m. Okay, qb divided by 2 pi m. Inverse of time period is frequency. Frequency equals qb by 2 pi m. Then angular frequency is given by omega, that is 2 pi f, 2 pi into nu. Omega equals 2 pi f, 2 pi nu, 2 pi into frequency. Okay, so 2 pi into nu, that we get it as 2 pi into qb by 2 pi m. So that on solving, we get qb by m. This is angular frequency. qb by 2 pi. This is frequency. This one is time period. So the time period is 2 pi m by qb. Frequency is qb by 2 pi m. And the angular frequency is qb by m. Now, what happens if velocity has two components? So this is velocity vector. This is a velocity vector making an angle theta with the horizontal, and the magnetic field is in the horizontal direction, positive x direction. The velocity vector is at an angle of theta with the horizontal. So obviously it will have two components, v cos theta as well as v sin theta. V cos theta as well as v sin theta, horizontal as well as vertical components. Okay. So the parallel component is v cos theta. Here the parallel component, it is v cos theta. And the perpendicular component will be v sin theta. Velocity vector will have two components. The quantity of charge here is q. Q is the quantity of charge taken, and it is having a velocity. And the velocity vector is inclined at an angle theta with the horizontal, and in the horizontal direction we have the magnetic field. And if this is the case, velocity at an angle to magnetic field, velocity, the charge is moving, or charged particle is moving with velocity v, and that velocity v is at an angle theta with the horizontal, or at an angle theta with the magnetic field. That's what you want to say. Then it is equal to it will have a vertical component as well as horizontal component. You see here, vertical component is written there. Horizontal component is also there. Two components are there. So the charge will execute circular motion due to the perpendicular component. Okay. Due to the perpendicular component, the charge will execute circular motion, and the circular motion will be perpendicular to the magnetic field. At the same time, it will move forward with a parallel velocity. That means v cos theta, the parallel velocity is also there. So it will move like this also. So in such a case, what will be the nature of the path of this charged particle? Okay. So here mv square by r, that is a centripetal force, it will be balanced by magnetic force, that is q into v perpendicular component of this one, that is v perpendicular. So that force will be balanced by m v perpendicular square divided by r. Okay. From that we get an equation for r. Equation for r will be mv by qb. One v perpendicular and one v perpendicular will be cancelled here. So this will be mv by qb will be equal to r, radius of the circular path in which the charged particle moves. Okay. Okay. Then this v perpendicular, we know v perpendicular equals v sin theta. V perpendicular there, v perpendicular equals v sin theta. So when we substitute the value of v perpendicular with v sin theta, we get mv sin theta divided by qb. Okay, next one. Time period. It is equal to 2 pi r divided by velocity. That will be equal to instead of r we can write mv by qb is r. We can write mv by qb. Okay, so if we write mv by qb instead of r, we get 2 pi mv by qb. Okay, then v perpendicular here. So this is the equation for time period. See here. Here again we can cancel that v perpendicular and we get 2 pi m divided by qb as the time period. So time period can be taken as 2 pi m divided by qb. Right? Now, so that was the case with the perpendicular component of the velocity. All perpendicular component of velocity we have taken here and we have developed an equation for the time period, and time period is equal to 2 pi m divided by qb. Now we have to see the parallel component of velocity. What happens to the parallel component of velocity and what is the impact of that parallel component in this? Because of the parallel component of velocity, this particle will have a transverse motion along the direction of magnetic field. Okay. Okay. It will undergo a circular path, but since it is having a horizontal velocity or a parallel velocity, the charge will have a transverse motion along the direction of magnetic field in addition to the circular motion. The circular motion is due to the vertical component or the perpendicular component. Okay. So due to the combined effect of circular and transverse motion, charge will move along a helical path. Okay. It will move along a helical path. Like this. It will move like this. So this circular motion is due to the v perpendicular and the helical motion, this horizontal motion, is due to V parallel. And the distance moved along the magnetic field in one time period, distance moved along the magnetic field in one time period is called pitch P. Now, what happens if the electric and magnetic fields are perpendicular to each other and also perpendicular to the velocity of the particle? Here, the velocity vector is towards right, electric field is upward, magnetic field is again at an angle of 90 degree with velocity. See here, velocity vector is towards right, electric field vector is upward at an angle 90 degree with the velocity. Magnetic field vector is again making an angle 90 degree with velocity. Now, in this situation, what happens? Let us see. So, total force will be equal to Fe plus Fm. We know total force for electric force plus magnetic force. And Fe equals Q multiplied by electric field, charge multiplied by the electric field, and Fm will be equal to Q into V cross B that we have seen just now, Q into V cross B. And electric and magnetic forces are in opposite direction. The total force on the charge is 0. Means E and B are in opposite direction, then the total force will be 0. And the here QE, force due to electric field, and QVB, force due to magnetic field, both are equal. Force due to electric field and force due to magnetic field are equal. Okay. So that is the case of velocity selector. QE equals Q into V cross B. Then velocity will be equal to E divided by V. Ratio of electric to magnetic field will be the velocity. Just see the board. All right, we move on to the next section of this chapter. Force between two parallel long current carrying conductors. When two current carrying conductors we keep like this, if they carry currents in the same direction, will they attract each other or repel each other? If they carry currents in opposite direction, will they attract each other or repel each other? That we are going to see now. Two current carrying conductors are there, PQ and RS. Two current carrying conductors written drawn there. One is PQ carrying a current of I1 and RS carrying a current of I2. They are separated by a small distance R. All right. So this is developing a magnetic field. The second one, I2, is developing a magnetic field B1, which is inward. See, it is backside of an arrow. So B1 is inward. So B1 will be equal to mu 0 I1 by 2 pi r. See here, the current carrying conductor, first current carrying conductor is PQ. This PQ carries a current of I1. This develops a magnetic field at this point, which is inward. To find this nature of magnetic field, there is a simple method. Hold your right hand like this. Thumb is the direction of current. This is the distance. And the face of this palm is the direction of magnetic field. There is no name for this rule, but this is a simple technique to remember. Like this. Thumb indicates the direction of current. This is the distance and the direction of the palm. See, the palm is inward. It is inward. So at this point, magnetic field B1 will be inward. Once again, like this. Thumb indicate the current. This is the distance and the phase is inward. So magnetic field B1 will be inward. So B1 will be equal. Remember, B1 is the magnetic field produced by the first current carrying conductor PQ at the point here, at the point X. So B1 equals mu 0 I1 by 2 pi r. R is the distance between these two. I1 is the current in the first conductor. Now, at B1 is a magnetic field developed by the first current carrying conductor. At B1, the second current carrying conductor is situated. Second current carrying conductor is situated in the magnetic field produced by the first current carrying conductor. So if a current carrying conductor is placed in a magnetic field, definitely it will experience a force. Okay, no? It will experience a force. Let us see. The force experienced by the second current carrying conductor situated in the magnetic field B1 produced by the first current carrying conductor, it is F21, F of 2, force of 2 due to current in the first, that is F21. Any force can be written as IL cross B. So B here is mu 0, that is B1. B here is B1. Then I is I2, the current carried by this second conductor, that is I2 into L. Okay. Then on solving, we get B1. We will substitute the value of B1, mu 0 I1 by 2 pi r. Mu 0 I1 by 2 pi r. When we substitute, the angle theta, angle theta is 90 here. IL and B. Angle between IL and B. B is inward. Inward. It is inward and IL is upward. So inward, upward. So this angle. So this is upward, the pen is inward. Okay. So this angle will be 90 degree. So sine 90 is 1. So we avoid this. And we get an equation F21 equals mu 0 I1 I2 L divided by 2 pi r. Mu 0 I1 I2 L divided by 2 pi r. And for unit length of conductor, length is unity. Unit length of conductor means theta equals 90. Then L is equal to 1 meter. That is the meaning of unit length of conductor. L is equal to 1 meter. So the force will be equal to mu 0 I1 I2 divided by 2 pi r. Mu 0 I1 I2 divided by 2 pi r. This is the force with which second force experienced by the second conductor, which is placed in the magnetic field produced by the first conductor. Then the direction of the force, which is obtained by the Fleming's left-hand rule. The force force on 2 due to the magnetic field by 1. So F21 will be towards left. This can be shown by the Fleming's left-hand rule. I upward, B inward, I upward. You can see this I upward, B inward, and force is towards left. Fleming's left-hand rule. FBI. Okay, now see this one. FBI. I is upward. You can see the diagram. Current is upward. Magnetic field is inward into the plane of the board. Now this is like this. I is upward, B is inward, force is towards left, like that. We can prove. So direction of the force is towards left. That means if two current carrying conductors are there, kept parallel to each other, and if the two current carrying conductors are carrying currents in the same direction, then the second conductor will experience a force towards left. What about the first conductor? What about the first conductor then? First conductor, here the current is upward, magnetic field is like this, magnetic field is like this. So I is upward, magnetic field is I is upward, magnetic field is out of the plane, force will be towards right. Okay, na? I is upward, magnetic field is out of the plane. This is I. This is B, magnetic field out of the plane, and the force is towards right. You can also see from this one, IL. What is the unit vector for IL? It is J. J cross B. B is like this K. J cross K is equal to I. It is towards right. And in the first case, F is equal to IL cross B. So here IL is upward, that is J cross magnetic field is inward into the plane of the board, that is minus K. So that is equal to minus I. So in the case of second conductor, force is towards left. In the case of first conductor, force is towards right. So these two experience a force towards each other. It experience a force towards each other. So if they experience a force towards each other, they will definitely attract each other. So if two current carrying conductors carry currents in the same direction, they will definitely attract each other. With how much force, that we are going to see, with how much force they are attracting each other, the force equals mu 0 I1 I2 by 2 pi r. So force here is mu 0 I1 I2 divided by 2 pi r. Just remember this, force is mu 0 I1 I2 by 2 pi r. We are moving to the next slide. You can write here F is equal to mu 0 I1 I2 divided by 2 pi R. I1 and I2 are the currents in two conductors. R is the separation between the conductors. Now let's see. B2 is magnetic field due to the second conductor. It is mu 0 I2 by 2 pi R. Force per unit length of PQ. Force per unit length of PQ, it is mu 0 I2 I1 by 2 pi R. Mu 0 I2 I1 by 2 pi R. The two forces are equal and opposite. Force on this one and force on this one. This will be towards right and this will be towards left. Okay. So this is F21. This is F12. Two forces are equal and opposite. They will attract each other. And if we take, so the general force equation is F equals mu 0 I1 I2 by 2 pi R. If we take I1 equals I2 equals 1 ampere and R is equal to 1 meter, I1 equals I2 equals 1 ampere and R is equal to 1 meter, then the equation reduces to F equals mu 0 by 2 pi. So the general equation for force, F21 equals F12 equals mu 0 I1 I2 by 2 pi R. And if I1 equals I2 equals 1 ampere and R, the distance of separation between the two, equals 1 meter, then F will be equal to mu 0 divided by 2 pi. We have a general value for mu 0 4 pi. It is equal to 10 power minus 7. So mu 0 by 4 pi equals 10 power minus 7. So mu 0 divided by 2 pi can be written as 2 into 10 power minus 7. Okay, so we can define ampere now. So we started with two conductors, two current carrying conductors, carrying currents 1 ampere each, separated by a distance of 1 meter apart. Okay, so 1 ampere is the current which passing through two parallel conductors of infinite length and placed 1 meter apart. So if 1 ampere is a current passing through two parallel conductors placed at 1 meter apart, separated by 1 meter apart, they're having infinite length. Length is not finite, infinite length they have. They exert a force of 2 into 10 power minus 7 Newton. Exert a force of 2 into 10 power minus 7 Newton per meter. On each meter, it exerts a force of 2 into 10 power minus 7 Newton on each other. So this is the definition for ampere. Okay. So remember, if two parallel current carrying conductors are there, if they carry currents in same direction, they will attract each other. And if they carry currents in opposite direction, they will repel each other. The force with which either they attract or repel, it will be equal to 2 into 10 power minus 7 Newton. And if they carry 1 ampere each and kept at a distance of 1 meter apart. So we define 1 ampere based on this. 1 ampere is that current which is passing through two parallel current carrying conductors of kept at a distance of 1 meter apart, either attract or repel with a force of 2 into 10 power minus 7 Newton per meter. Now, magnetic dipole moment of a circular current loop. We have a circular current loop. Current loop is very simple. A loop which carries a current I. We have a loop here which carries a current I. The loop is having an area capital A, carrying a current I. Next one is it will act like a magnetic dipole. So this is a current is circulating like this. It will act like a magnetic dipole. The magnetic dipole moment is given by the equation I multiplied by A. I is the current and A is the area vector. And if the coil has n number of turns, capital N number of turns like this, instead of one turn, it will have a large number of turns like this. N number of turns. N turns are there. If it is so, the magnetic dipole moment will be equal to N times IA. Then, similar is the case with the revolving electron. Electrons are revolving around the nucleus. Electron is having a charge, and if a charge is moving, it will constitute a current. So this circle is possessing, so having a current. So electron is equal to a current loop. Okay. So if it is moving like this, see, if it is moving like this, it constitutes a current. All right. So if it is so, let t be the time taken by the electron. Let t be the time taken by the electron to complete one rotation around the nucleus. And v is the speed. V is the speed with which the electron is moving around the nucleus. T is the time period, time taken to complete one rotation. And V is the speed with which the electron is moving around the nucleus. If it is so, current formed due to the movement of electron in a circular path around the nucleus is I equals E divided by T. General equation for current is rate of flow of charges. So charge is E, single electron, divided by the time taken for one complete rotation. One complete rotation, it is capital T. So it will be E by capital T. So the time period of electron is total distance. Total distance is, the radius here is R. So the total distance will be 2 pi R. Total distance 2 pi R divided by velocity. That will be the time period of electron. Then the current will be equal to E by T. Okay, E is as it is. Instead of T we write this one 2 pi R by mv. Sorry, 2 pi R by V. Instead of T we are writing 2 pi R by V. Then we get EV by 2 pi R. Current equals EV divided by 2 pi R. Electron is revolving around the nucleus. It constitutes a current. Since electron is having a charge and it is moving around the nucleus, it constitutes a current. The current is equal to E by capital T. Capital T is the time period for one complete rotation. Then instead of that, capital T can be written as 2 pi R divided by V. Total distance divided by total velocity. So we get an equation for the current. It is EV by 2 pi R. The magnetic moment produced by the movement of electron, it is equal to I multiplied by A. For I we have an equation. I is EV by 2 pi R. I equals EV by 2 pi R multiplied by A. So we substitute these values here and we get an equation for the magnetic moment as EVR by 2. And magnetic moment, we got an equation EVR divided by 2. then we are multiplying and dividing this equation with mass of an electron. Multiplying and dividing this equation on numerator as well as denominator, we introduce a quantity called mass of the electron. Then we get E multiplied by MVR divided by 2M. MVR, you may be remembering what is MVR. See here, mu L equals E into MVR by 2M. E into E multiplied by MVR divided by 2M. Okay. Then by Bohr postulate, Bohr's postulate, angular momentum L equals NH by 2 pi. Okay. This one, mu L equals E into MVR by 2M. Then the angular momentum is equal to NH divided by 2 pi. We are substituting this value here. We get E into NH by 4 pi M. Instead of L, we put NH by 2M. Instead of L, we put NH by 2M and we get E into NH by 4 pi M. Okay, for an electron in the first orbit of hydrogen atom. So there the N equals 1. If N equals 1, we can put N equals 1 in this equation. E into NH by 4 pi M. Then mu L will be equal to EH divided by 4 pi M. N equals 1 in this equation. This is called Bohr magneton. N is equal to 1 state. N is equal to 1 state. This one will be equal to EH by 4 pi M. And this is called Bohr magneton. Okay. We move forward. Bohr magneton is the magnetic moment produced due to the motion of an electron in the first orbit of hydrogen atom. It is called Bohr magneton. The value of this Bohr magneton is 9.27 multiplied by 10 power minus 24 ampere meter square. Now, another important concept, torque on a rectangular current loop in a uniform magnetic field. A rectangular current loop is kept in a uniform magnetic field. How much will be the torque experienced by the rectangular current loop? Let us see. Rectangular current loop carrying a steady current I and placed in a uniform magnetic field, it experiences a torque. And how it experiences a torque, let us see. We have a rectangular current loop ABCD. Rectangular current carrying loop is placed in a magnetic field. That means between the pole pieces of a magnet, that is north pole is here and south pole is on the other end, and between north and south pole we are keeping a rectangular coil ABCD. The field exerts no force on the two arms AD and BC of the loop. AD and BC of the loop. The reason is F equals IL cross B. Magnetic field direction is from north to south. This is the direction of magnetic field. Here, the direction of current is like this. So, BC side, theta equals 0 because current is going in this direction. Magnetic field is also in this direction. So, this is IL direction. This is B direction. So, theta equals 0. Force is also equals 0. Similar is the case with AD direction. AD, AD direction, current is like this, magnetic field is like this, B, and this is the direction of current. So here theta equals 180. Here also force will be equal to 0. So two sides, one is side BC and the second one is side AD. It will not experience any force. So other two sides, AB as well as DC, it will experience force. What will be the force experienced by AB? Current is going in this direction, magnetic field is in this direction. Then it will experience a force which is directed into the plane. That means downward into the plane of the loop. And in this case, DC, the current is opposite. If on this side, if this one experiences a force which is into the plane of the loop, if the side AB experiences a force which is into the plane of the loop, see here, the current here is in opposite direction. This DC will experience a force out of the plane of the loop. So here the force is inward, here the force is outward. This will go for a rotation. This will go for a rotation. Once again, I'll make it more clear. Force is IL cross B. BC is parallel to the side BC. Here, IL, the direction of current is towards right. Direction of magnetic field is also towards right because direction of magnetic field is always from north to south. So here the angle is 0. Force is also 0. Here the angle is 180. Force is again 0. So the force will be experienced by the sides AB as well as CD. In the side AB, current is upward, magnetic field is towards right. Current is upward, magnetic field is towards right, and it experiences a force into the plane of the loop. So AB side experiences a force into the plane of the loop. Here the current is opposite. It will experience a force out of the plane of the loop. So this will go in, this will come up. So it goes for a rotation. See this one? So F1 equals ILB. On the other arm CD, it is F2. On the other arm CD, the force is F2. F2 will be equal to again ILB. So one will come out and one will go in. F2 and F1 will be equal to ILB. Both will be equal to ILB. So net force on the loop is 0. Net force on the loop is 0. But the rectangular loop experiences a torque because on one end of the loop, it is upward. On the other end of the loop, one side of the loop, it is upward. And on the other side of the loop, it is downward. So it will go for a rotation. It experiences, see, you have to concentrate on this statement. It experiences a torque because the line of action of these two forces are parallel to each other. The line of action of these two forces are parallel to each other, just like so this will go up, this will go down. This is one force, this is another force, F1 and F2. but these two forces are, the line of action of these two forces are parallel to each other. F1 and F2 are parallel to each other. So torque will be equal to torque will be equal to force into perpendicular distance. So this F1, the perpendicular distance is a by 2, plus F2, perpendicular distance is a by 2 here. Force is IL cross B. So a by 2 into ILB plus a by 2 into ILB. So it becomes A into ILB. See here. IAB. I is the current, A is the area, and B is the magnetic field. Then, of course, this IA. Torque equals M cross B. This is another view. See, in vector form, torque equals IAB sine theta. IAB sine theta can also be written as IA cross B. And instead of that IA, we can write if there are n turns, if the coil has n number of turns, then we can write it as NIA cross B, number of turns multiplied by IA cross B. Okay, see this one. Total torque acting on this one will be NIA cross B. Now, next is moving coil galvanometer. Moving coil galvanometer is a device used to detect electric current in a circuit. Feeble electric current in a circuit. Okay, it has got a coil wound over soft iron core. Magnet is there, horseshoe magnet is there, soft iron core is there, then it is connected to external terminals, and there is a dial. The principle of moving coil galvanometer is a rectangular current carrying coil placed in an external magnetic field experiences a torque. Rectangular current carrying coil placed in a magnetic field experiences a torque. This is the working principle of moving coil galvanometer. Then constructional details. How can we construct a galvanometer? You see this one? It's the constructional details of a galvanometer. Galvanometer consists of a coil with many number of turns. So this is a coil with many number of turns, free to rotate about a fixed axis. Okay, free to rotate about a fixed axis. A needle is placed, attached with that. Then coil is suspended by a phosphor bronze wire. Okay, the spring made of the same material is attached to the coil at the bottom side. The duty of the spring is to bring back to the original position after deflection. When a current flows through the coil will rotate. When the coil is rotating, this needle also will be rotating. The torque on the coil is NIAB sin theta. NIAB sin theta, that is a torque on the coil. That means when a current is passing through the coil, when a current is allowed to pass through the coil will rotate because it experiences a torque. The coil experiences a torque, and as a result of the torque experienced the coil, it will rotate, and the rotating torque is equal to NIAB sin theta. The torque becomes maximum. Obviously, if theta is 90 degrees, sin theta will be equal to 1, and the torque becomes maximum, and the maximum torque will be equal to NIAB. See, the shape of the magnet is concave shaped. This is to maintain a radial magnetic field. So magnetic field is to be radial. To provide the radial magnetic field, we keep the shape of the magnets on both sides of the coil as curved shape, concave shape. So concave shape magnet is used to provide radial magnetic field. All right, let us move on. Magnetic poles and a soft end cylinder is kept inside it. See, this is the radial magnetic field. If we keep the shape like this, it becomes radial. See this one? Now, in a radial magnetic field, theta will be equal to 90. So the torque will be equal to NIAB. N is the total number of turns, I is the current, A is the area, and B is the magnetic field. The torque will rotate the coil through an angle phi. Okay. This torque will twist the suspension fiber. Of course, that also will be twisted by an angle phi. That deflecting torque as well as restoring torque, both will be equal. Deflecting, one, the current is trying to deflect the torque, and the coil is trying to restore the galvanometer to the original location. All right. So these two things, it is given by the torque required to twist the suspension fiber through an angle phi is given by C phi. Okay, C phi. C is the torque required to twist through unit angle, and both will be equals. One is the deflecting torque, and the second one, this one is a deflecting torque, the torque which is trying to deflect the coil, and the second one is restoring. If the current is absent, this will try to restore the coil to the original position. Both will be equal. And we can see that current I equals, from this equation, we can say that current I equals C phi divided by NAB. C phi divided by NAB. N is the number of turns, A is the area of the coil, and B is the magnetic field. C phi divided by NAB. That is the current, value of current. Here we can see I equals C by NAB phi. C is a constant, N is a number of turns, area, and magnetic field. So this can be made as a constant. So we can say that I proportional to phi. Current is proportional to the deflection. I is a current which is proportional to the deflection phi. So that is the basic working principle of a galvanometer. The current flowing through the galvanometer will be proportional to the deflection produced in the galvanometer. G is called the galvanometer constant. G equals, the value of G equals C by NAB. Now the current sensitivity of a moving coil galvanometer. Deflection per current is given by the relation I is equal to C by NAB multiplied by phi. So current sensitivity is deflection per unit current. How much deflection is there for 1 ampere current? That is called current sensitivity. Deflection per unit current. Okay, phi divided by I. So phi equals NIAB divided by C. Phi by I equals NAB. So here we can write phi equals NIAB into C. Then phi by I equals NAB, divided by C. Okay, so phi by I equals NAB divided by C. Now, next is the voltage sensitivity. So, current sensitivity is the deflection per unit current. You can see the current sensitivity as the deflection per unit current, deflection upon current. That means if 1 ampere current is flowing through the galvanometer, how much deflection it produces? Unit current is 1 ampere current. If 1 ampere current is flowing through the galvanometer, how much deflection the galvanometer produces? That is called current sensitivity. Now, voltage sensitivity. So, deflection produced by the galvanometer for unit voltage. That is called voltage sensitivity. So, the equation for voltage sensitivity is phi by V. Phi by V can be written as I multiplied by R. So, similarly, you can substitute the values and we will get a relation like this, NAB by C into 1 by R. See here, current sensitivity is phi by I, that is NAB by C. Voltage sensitivity is NAB by C into 1 by R. So, if you divide current sensitivity with the resistance, you will get voltage sensitivity. Remember, current sensitivity and voltage sensitivity means how much deflection we get for unit current, that is current sensitivity, how much deflection we get for unit voltage, that is called voltage sensitivity. Then how can we convert a galvanometer into an ammeter? It's very simple. This is a galvanometer. Conversion of a galvanometer to an ammeter. So this is a galvanometer. By connecting a parallel low value resistance, when connected in parallel, then it becomes an ammeter. A low value resistance is connected in parallel. That becomes an ammeter. See here, the current entering here is I. Ig is flowing through the galvanometer. I minus Ig is coming through this resistance. Resistance is a low value resistance, which is called as a shunt resistance. Potential difference across this galvanometer is Ig into G. Here it is Ig multiplied by G. Here it is I minus Ig multiplied by S. Both are connected in parallel. Okay, both are connected in parallel. So both the potential differences will be equal. So Ig multiplied by G will be equal to I minus Ig multiplied by S. There we get S, the value of S equals Ig into G divided by I minus Ig. Then how can we convert a galvanometer to a voltmeter? So the method is very simple. We can connect a high value resistance in series with a galvanometer to make the galvanometer into a voltmeter, or convert a galvanometer into a voltmeter. A high value resistance which is connected in series with a galvanometer. This is a high value resistance. In the other case, in the case of ammeter, a low value resistance was connected in parallel to galvanometer, which made the galvanometer into an ammeter. Here, a high value resistance is connected in series with galvanometer to make the galvanometer a voltmeter. See this one, a high value resistance connected in series. Okay. The current flowing here is Ig. This develops a potential difference across this G, that is Ig into G. And here it is again Ig multiplied by R. So total voltage will be equal to Ig into G plus Ig into R. Ig multiplied by R. Both are in series combination. This galvanometer and high resistance are in series combination. So it will be the sum of individual voltages. We get the value of R to be connected to make the galvanometer and a voltmeter. So that is, we get the value as V by Ig minus capital G. V by Ig minus capital G. So in this method, we can convert galvanometer into a voltmeter as well as ammeter. V is the maximum voltage which can be measured by using that galvanometer. Ig is a maximum current which we can send through the galvanometer. Of course, G is the galvanometer resistance. Okay, here we stop for today. Again, we will meet tomorrow morning at 6:30. And if at all any doubts or anything is there in this particular chapter, you can SMS me, or you can send messages, or even you can put it in the chat box today, tomorrow, day after tomorrow, anything like that. Okay, hope you enjoyed the session. Thank you. Good night. Other